All right, in this lecture, we're going to talk about catalytic rate laws. And specifically, we're going to talk about rate law for a particular example. Say we have some reaction, 2A goes to B, it's carried out in the gas phase. But this is, rather than being carried out homogeneously, this reaction is going to be carried out on a catalyst. And because of that, the form of the rate law looks like this, which is slightly different than the power law rate laws that we have been looking at. So in this lecture, we're going to kind of cover why that is. Okay, so some of the things. What is different about this rate law compared to the ones that we've been looking at? Let's see here. Okay. This rate law here is takes the form of a Langmuir-Hinschelwood type rate law. So part of the Langmuir-Hinschelwood formalism is that it comprises information about the free site coverage and the rate determining step. So specifically, I'm going to show you in this lecture that this term here inside the parenthesis is the free site coverage. Well, actually, 1 divided by that is the free site coverage. And then the rate determining step has something to do with this term here. So that is actually going to have something to do with the rate determining step. I'm not going to show the rate determining step piece here. We're going to talk about that in a later lecture where we go into the rate determining step method in detail, but I am going to show how this denominator term comes into play. So the Langmuir-Hinschelwood type rate law comprises information about the free site coverage and the rate determining step. So those are both embedded there. So some differences between this rate law and the ones we've been thinking about in CBE 3610. One simple one is that this rate law is given in terms of pressure. So you see it's pressure of A and pressure of B, where typically we are used to the rate law being given in terms of concentration. But we also know this is a gas phase reaction and that pressure and concentration are related for gas. So recall for gases that concentration is equal to P over RT. So it's a restatement of the ideal gas law. That's like saying N over V is equal to P over RT. And a lot of times in catalytic reactions, if the fluid phase, if the reacting species are gas phase species, the rate law will be given in terms of pressure. The other difference is that in this rate law here, there is an equation in the denominator. And not only is there an equation, but this equation is not a simple power law function. So we've got a sum of things. We've got some things involve constants that we're used to, capital K's, equilibrium constants, P's are pressures, but we've also got this value of 1 here. What is that doing here? So this is different than the power law rate laws that we've been looking at. And this arises because the reaction takes place on the catalyst surface. And the catalyst surface has a finite number of sites on which the reaction can happen. So when I say a catalyst site, that's going to be a location or a chemical identity on the catalyst where the reaction can take place. And I'll explain what that is in just a second. So there's many examples of catalysts. So catalyst sites can take on many forms, many different compositions. Maybe an easy to understand or relatively easy to understand example is if your catalyst is a metal particle. So let's say we have a platinum particle and that's our catalyst. These types of catalysts are common because they are used in the catalytic converters of a variety of cars. So if our catalyst is a metal particle, then a catalyst site might be just one atom on the surface of that metal particle. So let's see here. If we have a catalyst particle, I'm going to draw this. So we talked in the last lecture about how if you have a catalytic reactor, then it's packed with pellets, and that the pellets have catalyst deposited within their pores. So I'm going to draw this here. This is a pore surface. So within the pore, this is the surface within one of the many pores within that catalyst pellet. And then I have on there some support material. For example, alumina. And then on the support, I have deposited a platinum particle. And this platinum particle here, this is just a chunk of platinum metal. Probably a pretty small chunk. They tend to be on the order of nanometers, maybe like 1 to 10 nanometers in size. And so if we zoom in, what we would see, so maybe we are going to zoom in to like that region. If we zoom in, what we're going to see from the top is a bunch of metal atoms. And if we look at the side, maybe I'll probably looks about the same, but I'll make them distinct in just a second. So now I have this is some thickness in the second view. These are a bunch of metal atoms. And each atom is a site. So we can illustrate this. The platinum metal atom will easily dissociate an oxygen molecule. So because of that, platinum catalysts are used a lot in oxidation reactions because we can take oxygen, maybe even oxygen from the air, and put it in the presence of a platinum catalyst, and the platinum catalyst will easily break that oxygen-oxygen bond. So that allows us to provide or perform oxidation reactions in a much energetically easier way than if we had to do that in the gas phase. So if I had the same surface here, so my top, I'll take my side view. And I am going to interact this with an oxygen molecule. So I have an oxygen molecule, and this is going to interact with the catalyst surface. Let me see if I can copy this here. So this oxygen molecule is going to form a chemical bond with the catalyst surface. So what we saw here is oxygen adsorbing to the catalyst surface. And then what the catalyst surface will do is very easily dissociate this molecule. Into two oxygen atoms. So what I've done here is draw a reaction. So this is I have oxygen, actually I've drawn two reactions. I have oxygen in the gas phase, and that has adsorbed to the catalyst. It has adsorbed to one site, and then it has dissociated. So my adsorbed oxygen now forms two my adsorbed oxygen molecule now forms two adsorbed oxygen atoms. So I'm going to explain this notation in just one second, but what we see here is that this platinum atom, where this oxygen adsorbed, it acted like a catalyst by dissociating the oxygen molecule. So that atom is a catalyst site. It is a place where part of a oxidation reaction happened. When I wrote these reactions, I introduced two new forms of writing things. One is this asterisk. That denotes a catalyst site. So in this case, a platinum atom. And when I have a starred species, such as this one here, or this one here, actually, I do that second line too long. I have O2 star and I have O star. Those species are bound to a catalyst site. So to illustrate that, consider this reaction 1 here. I start out with a gas phase oxygen molecule. It collides with the surface and forms a bond. That's what's going on in this reaction here. Okay. I guess I could have written all of this over here. I had plenty of room, but okay. So anyways, getting back to this. This denominator term here, this is going to tell us the free site coverage. So the free sites are all of the sites on the catalyst surface that don't have something in them. So, and that's going to be important because those are the ones where the reaction can be taken out. So this denominator term is actually a coverage term. It tells us something about the fraction of free sites on the catalyst surface. So here I'm talking about coverage, which is probably a new term. So what is coverage? So we will explore this in this class more later, but for now, I want to give an illustration of coverage. So this presentation here, I've drawn a catalyst surface, and I've drawn a gas molecule adsorbing on the catalyst surface. So we have this the catalyst surface is in gray, and the gas molecule is just a red circle or sphere. It can be the oxygen molecule, it can be something else. So one term, or two terms that we will talk about when we get more into catalysis are the terms adsorption and desorption. Adsorption is basically a gas molecule forming a bond with the catalyst surface, and desorption is breaking that bond and the molecule going back into the gas phase. So pictures of those things are here. You see the gas molecule adsorbing, that collides with the catalyst surface. It forms an adsorbed molecule, which can then the adsorbed molecule can then stay on the catalyst surface, or it can desorb. So that's what's going on here. In a real system, I would have multiple molecules doing that. So this is a top-down view of the catalyst surface. As you can see, I have some number, I can count them 8 molecules on the surface. I have a couple of molecules on the catalyst surface, but nowhere near full. I would call this a low coverage surface because the number of adsorbate molecules is slow. So coverage is basically what fraction of this catalyst surface has adsorbates on it. And then the remaining fraction is the free catalyst surface where catalytic reactions can occur. So if a molecule is taking up space on the catalyst, that means that no reaction can occur there. The reaction is going to occur on the free regions of the catalyst surface, so the gray regions in this picture. This is a low coverage surface because I only have a little bit of or a small number of adsorbates on the surface. If I can look at a more populated catalyst surface, that might look something like this. So I have a lot of molecules on the surface, and my free space, the gray regions, has decreased dramatically. If I go all the way up and completely fill my catalyst surface, it might look something like this. So in this case, this surface is completely filled, and it will not carry out catalysis because there's simply no place to do that. There's just adsorbates sitting all over the surface. So the concept of coverage is analogous to surface concentration. So what is the number of molecules on the surface per unit area, or what is the number of molecules on the surface per site? So we can write coverage in two different ways. In the latter of those, we would say I have some number of sites on the catalyst. What fraction of those are filled? That would be, when we say the fraction that are filled, we say we're talking about fractions of a monolayer. So a monolayer is when I have one adsorbate per site on the surface. So every single site is filled. That's what this picture here is showing. What this says is that I have one molecule per site. That's my coverage. Every site has a molecule in it. I can, for this particular catalyst, this is just something I drew in PowerPoint, so I know a lot of the details about it. I drew a rectangle as a top view of my catalyst, and I populated it with these red circles. I counted up the circles, and if I counted correctly, which isn't really guaranteed, but let's pretend I did, it has 312 sites, and that means I can fit 312 of these red molecules on this surface. So if I go back to my low coverage representation and my moderate coverage representation. In my low coverage representation, I said that I only had 8 molecules on the surface, but I also know that I have 312 total sites. So if I wanted to know the coverage in fractions of a monolayer, I simply divide 8 by 312. I get 0.026. So this is a pretty low coverage surface. Only about 3% of the sites are filled, and that leaves about 97% of the sites for available to carry out the catalysis. I can also write surface coverage in terms of surface area, so how many molecules per unit surface area. So that's what I am doing here. If I take this catalyst surface, and measure the surface area. And literally here to create this representation, I basically just had PowerPoint tell me the dimensions of this rectangle I drew, and I used those to calculate a surface area. So, and then it told me that, and by doing that, I got an answer of 233 square centimeters. So if I have a catalyst and it has some surface area and I have some number of adsorbates on it, another way that I can write coverage is to say I have 8 molecules for over a 233 square centimeter surface. That means that my coverage is equal to 0.034 molecules per centimeter squared. So 2 different ways that I can write coverage. And maybe this second one is it makes a little bit more sense how this is a concentration term. So instead of a gas phase concentration where I would have moles per volume, here I have molecules per unit surface area, because it's a 2-dimensional surface. We tend to use the monolayer representation more because it tends to be a little bit easier for various applications. We'll get into some of those later in the class. But the other part about that is that typically I would know the number of sites per unit area, so I can easily convert between the monolayer representation and the per surface area representation. Okay, so I've just shown how we can calculate the coverage of adsorbates on a surface. For catalysis, we are often interested in the free site coverage because that is where the reaction can occur. If I only have one type of adsorbate, then I can easily get the free site coverage if I know the adsorbate coverage, because the free site coverage is just what's left. So if I wanted to know the coverage of free sites in units of free sites per unit area, I simply take the total number of free sites minus those covered or those occupied by this red adsorbate here, and I can do that taking 312 total sites minus 8 that are occupied divided by 233. That gives me a free site coverage of 1.304 free sites per centimeter squared. Or in terms of monolayer coverage, I could say 312 total sites minus 8 that are occupied divided by 312, and that gives me a free site coverage of just over 97%. So, and that I could have gotten that also by taking 1 minus 0.026, which was the coverage of the red molecules that we looked at earlier. When I do this, what I'm essentially doing is I'm making a site balance. So I have a finite number of sites on my catalyst surface. Those sites can either have something in them or not. So when I sum the number of sites that have something in them with the number that don't, I should get either the total number of sites per unit area or 1 if I'm thinking about a monolayer basis. So this takes into account that the number of sites on the catalyst surface is finite. So this is an important feature, but it also gives us a way to calculate free site coverage if we know the coverage of adsorbates. So this entire development that I just showed you is based on just a single adsorbate. Of course, I can have multiple adsorbates. Here's an example of a case where I have 2. Now I have red adsorbates and blue adsorbates. And due to site balance, the same thing applies. The free sites is equal to, or takes the total number of sites and subtracts from that the number of sites that have something in them. In this case, it would subtract from that the sites that have red molecules and the sites that have blue molecules. So if I add up all of the sites that have red molecules with those that have blue molecules with those that have nothing, I should get either the site per unit area density or concentration, or I should get 1 if I'm thinking about monolayers. So in monolayers, what that would be saying is the fraction of sites with red molecules plus the fraction of sites with blue molecules plus the fraction of free sites is equal to 1. Okay, so that's coverage. I can have low coverage situations, I can have moderate coverage situations, I can have very high coverage situations. Coverage is the concentration of molecules adsorbed to the surface, and what I'm interested in is what's left on the surface, so the sites without molecules in them, so the gray regions, for example, in this picture and that picture, that is where the reaction can occur. Okay, so So coverage, long story short, is like a concentration variable. It tells us the number of molecules that are adsorbed to a surface. We'll say the number of sites tells us the number of sites on the catalyst surface that are occupied by adsorbates. So adsorbates are atoms and molecules that have formed bonds with the catalyst surface. We are interested in the free site coverage because that's where the reaction can take place. And that was those gray regions in the PowerPoint presentation that I just showed. So the free site coverage, we denote theta star. So in general, we denote coverage as with the lowercase Greek letter theta. The free site coverage is denoted theta star, so this star is this free site, and that goes back to this notation we used here. The star is a catalyst site. And what the free site coverage is the fraction of catalyst sites that don't contain adsorbates and hence are available to carry out or catalyze the reaction. So in the prior example, we saw that theta star was equal to, if we're thinking in monolayer terms, it's equal to 1 minus the coverage of red adsorbates minus the coverage of blue adsorbates. In this example, let's go back up here. We have a reaction, 2A goes to B. So conceivably in our system, there's going to be molecules of A and molecules of B. And conceivably, both of those have the opportunity to adsorb to the catalyst. So in our example, theta star is going to be equal to 1 minus theta A minus theta B if we're thinking in monolayer terms. And it would be theta star would be equal to theta total minus theta A minus theta B if we were thinking in terms of sites per surface area. But I'm going to use monolayer convention here because it's a little bit easier. So basically, some number of sites could possibly be covered with A, some number of sites could possibly be covered with B. Whatever is left, that gives me the free site coverage in our example. So now we need, if we want to know the free site coverage, we need expressions for theta A and theta B. So we're going to get these by considering the adsorption of these species on the catalyst. So adsorption occurs when a fluid phase molecule forms a bond, and this can be a chemical or physical bond, with a solid surface. In our case, that solid surface is a catalyst. So if I have my catalyst surface and I have molecules of A, for example, zooming around here, some of those molecules are going to collide with the surface. So these molecules are maybe zooming all around like gas phase molecules do. Trying to draw this kind of randomly. Some molecules are going to collide with the surface, so collide. And when the dust settles, you'll get a molecule of A bound to the surface. So we can write this reaction, A gas plus star goes to A star. We can do the same thing with B. I'll write that over here. So molecules of B in the gas phase, catalyst surface. So these molecules of B are kind of zooming around. One molecule of B collides with the surface. And when the dust settles, and there's really no dust at the molecular level, a dust particle would probably be much larger than these molecules. But I get this adsorbed B. So B gas plus star goes to B star. So all of these molecules here, these are my A gas. There's here in the catalyst, there's sites I haven't drawn in the detail, but there's sites on that catalyst surface, and then this species here, this is my A star. So in these cases, the fluid phase molecules, the gas phase molecules A and B, are forming a chemical bond with the surface. So when we're thinking about catalysis, one assumption that we make is that the gas phase molecules, so A gas and B gas, are in equilibrium with the catalyst. So what that tells us is that the rate of adsorption of the molecule is equal to the rate of desorption. So we can say 0 is equal to K F A P A theta star minus KR A theta A. That's a restatement of this reaction. A gas plus star goes back and forth to A star. So basically what I've done here is I've set up an elementary rate law for this reaction. I've written it in terms, for the gas phase species, I've written in terms of pressure rather than concentration, but we know that we can convert between those two things using the ideal gas law. And for surfaces, I've used, instead of concentration, I've used theta, which is coverage, which is also surface concentration. So I've just written here an elementary rate law. There's a little bit of different terminology due to the fact I've used pressure instead of concentration for my gas species, and I've used theta instead of C for my surface-bound species, but that's because theta is the term I use to denote surface concentration. So anyways, I can do this for both A and B. These K's, I should say, are lowercase k's. They are rate constants. The Kf's are rate constants for adsorption, and the Kr's are rate constants for desorption. So let's see here. Oops. So Ford Forward reactions are adsorption, reverse reactions, desorption. And anyways, I've said they're in equilibrium, so the rates are equal, and then we can write our equilibrium constants for these then. Ka is going to be equal to theta A over Pa theta star, and Kb is going to be equal to theta B over Pb times theta star. And I get that by basically simplifying these rate equations, or simply by the definition of an equilibrium constant. If this is my reaction, then I know that my equilibrium constant is going to be the concentration of A star divided by the pressure of a gas times the concentration of theta star, which is exactly what I've written here. The nice thing about this is it allows me then to write expressions for theta A and theta B. So theta A is going to be equal to Ka Pa theta star. Theta B is equal to Kb Pb theta star. We know that theta star is equal to 1 minus theta A minus theta B. Therefore, theta star is equal to 1 minus Ka Pa theta star minus Kb Pb theta star. And I can rearrange that. So I'm going to basically group my theta star terms, and if I do that, I can work some algebra to get this expression here, which is exactly this argument, or this term inside the parenthesis here, which is what I told you at the beginning of the class we were going to get to. So what this tells us is our rate law is actually equal to K times the pressure of A squared times theta star squared. And we will get to why that is when we look at mechanisms later in the class. But for now, when you see a rate law like such as this one, that's probably what it's telling you. If you have a term in the denominator that has some sum of terms that's not completely a power law, a 1 plus something is a key giveaway that this is a Langmuir-Hinschelwood type rate law, and that this term here, or 1 divided by that term, is the free site coverage. So one thing to note about coverage is it influences the rate. So this term here is essentially the coverage of A. This term here is essentially the coverage of B. And this term here is essentially the free site coverage. So if your surface is completely uncovered, there's no A or B on it, and it's all free sites, now your rate law reduces just to K times Pa. However, if you have A or B on the surface, then what's happening there is your free site coverage is reduced, and your denominator term is larger, and the consequence of that is that the rate is smaller. So we'll say up theta A and or theta B down negative Ra. And the reason for that is because A and B take up sites and hence inhibit the reaction. The more sites there are, the faster the reaction will go. So if you've got A and B bound to the surface, they're taking up sites where the reaction could occur, and because of that, they're making the rate slower. So this is an expression of the finite nature of the number of sites on the catalyst surface. There's only so many, so the coverage on the catalyst matters, because at a high coverage, there's not going to be very many sites available to carry out the reaction.